Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete function and structure of one of the most powerful and debated systems in modern engineering, the nuclear power plant. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone, only the steady voice of information. Now please sit back, close your eyes if you like, and let the story of the nuclear power plant begin. Nuclear power is a form of energy that has shaped the modern world in ways both subtle and profound. And to understand how a nuclear power plant works, it is necessary to begin with the very basics of what nuclear power actually is and why it matters. At its core, nuclear power relies on the energy stored inside the nuclei of atoms, the small but incredibly dense centers that make up every element. Unlike chemical energy, which comes from the interactions of electrons around atoms, nuclear energy is released when the nucleus itself changes in a process called fission. This process produces a large amount of heat, far greater than what can be obtained from burning coal, oil, or natural gas, and this heat can then be converted into usable electricity. The introduction of nuclear power into the global energy mix came during the 20th century, when scientists discovered that splitting heavy elements, such as uranium or plutonium, would release tremendous energy that could be harnessed for peaceful electricity production as well as for destructive weapons. The world quickly realized that nuclear power held the potential to supply large quantities of electricity without the constant need for fossil fuels, and this promise of nearly limitless energy captured the imagination of both governments and engineers. To understand nuclear power in a steady and structured way, one should begin with the simple idea that a nuclear power plant is essentially a machine that transforms the heat from atomic reactions into electrical energy through the same basic mechanical principles that apply in coal or gas plants. In every case, heat is used to turn water into steam, and that steam drives turbines, which are connected to electrical generators. What makes a nuclear plant unique is not the turbine or the generator, but the source of the heat. While a coal plant burns solid fuel and a gas plant burns hydrocarbons, a nuclear plant uses the energy released from atomic fission. The advantages of this approach are numerous, because uranium fuel can generate much more energy from a small amount of material, and the actual combustion of fossil fuel is not required, meaning that air pollution and carbon dioxide emissions are significantly lower. However, nuclear power also brings challenges such as radioactive waste, safety concerns, and high construction costs, which have made it a subject of constant debate since its earliest use. Even so, nuclear power remains an essential component of the global energy system, supplying electricity to millions of households and industries around the world, particularly in countries that lack abundant fossil fuel resources but require stable, large-scale power generation. When people speak of nuclear power, they often imagine complex machinery, glowing rods, or the cooling towers that release vast clouds of water vapor into the sky. Yet at the most fundamental level, the concept is remarkably straightforward. Energy is locked inside the nucleus of the atom. Scientists discovered how to release it, and engineers designed systems to control the reaction, use the heat, and convert that heat into the electricity that flows through the grid. This introduction provides a foundation for the detailed sections that follow, where each component of a nuclear power plant will be examined in slow and careful detail, from the reactor core to the cooling system, from the turbines to the safety barriers. The story of nuclear power is one of scientific discovery, engineering innovation, and societal debate, and it continues to evolve as new reactor designs are developed and as questions of sustainability and climate change influence energy policy worldwide. For now, it is enough to remember that nuclear power begins with atoms, continues with heat, and ends with electricity, lighting homes, powering industries, and sustaining modern life. The historical development of nuclear energy is a story that begins with the curiosity of scientists studying the atom in the late 19th and early 20th centuries, long before anyone imagined building a nuclear power plant. In the early years of atomic research, scientists such as Henri Becquerel, Marie Curie, and Pierre Curie discovered that certain elements emitted invisible rays of energy, which they called radioactivity. These discoveries revealed that the atom was not an indivisible particle, as once thought, but a structure with hidden energy inside. As research continued, Ernest Rutherford and others showed that atoms contained a dense nucleus, and experiments in the 1930s proved that bombarding uranium with neutrons could cause the nucleus to split apart, releasing both energy and additional neutrons in the process. This reaction, known as nuclear fission, was the scientific foundation for both nuclear weapons and nuclear power. In the 1940s, the world entered a new phase when the Manhattan Project in the United States built the first nuclear reactors as part of wartime research. These early reactors were designed not to generate electricity, but to produce plutonium for atomic bombs. Yet they demonstrated that controlled fission could sustain a chain reaction and release steady heat. Once the war ended, scientists and governments began to ask whether the same process could be applied to peaceful purposes. In 1951, the first electricity generated from nuclear energy was produced in Idaho, where a small reactor lit 4 light bulbs, marking the symbolic birth of nuclear power for civilian use. This was quickly followed by the construction of experimental and commercial reactors in the United States, the Soviet Union, the United Kingdom, and other nations. The 1950s and 1960s became a period of rapid development, with nuclear power promoted as the energy of the future, often described as too cheap to meter. Countries invested heavily in reactor research, building different designs such as pressurized water reactors, boiling water reactors, and gas-cooled reactors, each with specific advantages and challenges. By the 1970s, nuclear power plants were operating in many industrialized nations, supplying significant amounts of electricity and reducing dependence on imported fossil fuels. However, this period also brought new challenges, including concerns about safety, waste disposal, and rising construction costs. Incidents such as the partial meltdown at 3 Mile Island in 1979 and the disaster at Chernobyl in 1986 deeply influenced public perception, creating fear and skepticism about the technology. Despite these setbacks, other countries such as France embraced nuclear power, building dozens of reactors and making it the backbone of their energy supply. Meanwhile, Japan, South Korea, and other nations in Asia also expanded their programs, seeing nuclear energy as a way to ensure stability and security in electricity production. The development of nuclear energy is therefore a mixture of optimism and caution, of technological achievement and social debate. Each stage of its history reflects both the potential benefits of harnessing atomic power and the persistent concerns about risks and consequences. By the early 21st century, nuclear energy had established itself as a major source of electricity worldwide, though unevenly distributed, with some countries heavily reliant on it, and others rejecting it entirely. In the present day, the history continues to evolve as new designs, such as small modular reactors and advanced fast breeder reactors, are developed, promising greater safety and efficiency while addressing concerns about waste and sustainability. The story of nuclear energy is not only about physics and engineering, but also about politics, economics, and public trust. And it provides the essential background for understanding why nuclear power plants exist, how they were developed, and how they might change in the future. The historical development of nuclear energy is a story that begins with the curiosity of scientists studying the atom in the late 19th and early 20th centuries, long before anyone imagined building a nuclear power plant. In the early years of atomic research, scientists such as Henri Becquerel, Marie Curie, and Pierre Curie discovered that certain elements emitted invisible rays of energy, which they called radioactivity. These discoveries revealed that the atom was not an indivisible particle, as once thought, but a structure with hidden energy inside. As research continued, Ernest Rutherford and others showed that atoms contained a dense nucleus, and experiments in the 1930s proved that bombarding uranium with neutrons could cause the nucleus to split apart, releasing both energy and additional neutrons in the process. This reaction, known as nuclear fission, was the scientific foundation for both nuclear weapons and nuclear power. In the 1940s, the world entered a new phase when the Manhattan Project in the United States built the first nuclear reactors as part of wartime research. These early reactors were designed not to generate electricity, but to produce plutonium for atomic bombs. Yet they demonstrated that controlled fission could sustain a chain reaction and release steady heat. Once the war ended, scientists and governments began to ask whether the same process could be applied to peaceful purposes. In 1951, the first electricity generated from nuclear energy was produced in Idaho, where a small reactor lit 4 light bulbs, marking the symbolic birth of nuclear power for civilian use. This was quickly followed by the construction of experimental and commercial reactors in the United States, the Soviet Union, the United Kingdom, and other nations. The 1950s and 1960s became a period of rapid development, with nuclear power promoted as the energy of the future, often described as too cheap to meter. Countries invested heavily in reactor research, building different designs such as pressurized water reactors, boiling water reactors, and gas-cooled reactors, each with specific advantages and challenges. By the 1970s, nuclear power plants were operating in many industrialized nations, supplying significant amounts of electricity and reducing dependence on imported fossil fuels. However, this period also brought new challenges, including concerns about safety, waste disposal, and rising construction costs. Incidents such as the partial meltdown at 3 Mile Island in 1979 and the disaster at Chernobyl in 1986 deeply influenced public perception, creating fear and skepticism about the technology. Despite these setbacks, other countries such as France embraced nuclear power, building dozens of reactors and making it the backbone of their energy supply. Meanwhile, Japan, South Korea, and other nations in Asia also expanded their programs, seeing nuclear energy as a way to ensure stability and security in electricity production. The development of nuclear energy is therefore a mixture of optimism and caution, of technological achievement and social debate. Each stage of its history reflects both the potential benefits of harnessing atomic power and the persistent concerns about risks and consequences. By the early 21st century, nuclear energy had established itself as a major source of electricity worldwide, though unevenly distributed, with some countries heavily reliant on it and others rejecting it entirely. In the present day, the history continues to evolve as new designs, such as small modular reactors and advanced fast breeder reactors, are developed, promising greater safety and efficiency while addressing concerns about waste and sustainability. The story of nuclear energy is not only about physics and engineering, but also about politics, economics, and public trust. And it provides the essential background for understanding why nuclear power plants exist, how they were developed, and how they might change in the future. Nuclear fission is the central process that makes nuclear power plants function, and it is one of the most significant discoveries in the history of science and engineering. Fission is the splitting of a heavy atomic nucleus into two lighter nuclei, and it occurs when certain isotopes, such as uranium-235 or plutonium-239, absorb a neutron. The absorption of the neutron makes the nucleus unstable, and this instability causes it to break apart almost immediately into two smaller nuclei, known as fission fragments. During this splitting, a large amount of energy is released because the combined mass of the fragments and the emitted particles is slightly less than the original mass of the nucleus. According to Einstein's famous equation, E equals mc squared, even a tiny loss of mass corresponds to a large release of energy. This energy appears in the form of kinetic energy of the fission fragments, as well as radiation and heat. The heat is what is ultimately used in a nuclear power plant to boil water and produce steam to drive turbines that generate electricity. Another important feature of fission is that it releases additional neutrons, which can go on to strike other uranium nuclei. If conditions are right, these secondary neutrons cause further fission events, and a chain reaction is established. The ability to sustain a controlled chain reaction is the key principle behind every nuclear reactor. In an uncontrolled environment, such as in a nuclear weapon, the chain reaction grows exponentially in microseconds, leading to an enormous explosive release of energy. In contrast, a power plant uses reactor design and engineering controls to regulate the number of neutrons and maintain a steady rate of fission so that the heat is produced gradually and safely. Uranium-235 is especially useful as fuel because it has a high probability of undergoing fission when it captures a neutron, and the energy released per fission event is significant, usually around 200 million electron volts. This amount may sound abstract, but when multiplied by the trillions of atoms undergoing fission every second inside a reactor, the scale of the energy becomes clear. By comparison, the burning of a single molecule of methane in a gas plant releases only a few electron volts of energy. This enormous difference in energy density is why nuclear power can generate vast amounts of electricity from small amounts of fuel. The fission process also produces byproducts in the form of radioactive isotopes that remain unstable and continue to emit radiation for long periods. These fission products are a challenge in nuclear energy because they must be carefully managed and stored to prevent harm to people and the environment. Yet despite these challenges, the fundamental principle of fission remains elegant and powerful. A heavy nucleus captures a neutron, it becomes unstable, it splits into smaller parts, it releases heat, and it emits more neutrons, which continue the cycle. In the controlled environment of a reactor, engineers use materials such as control rods and moderators to manage this sequence, ensuring that enough fission events occur to produce continuous energy. But not so many that the reaction becomes unsafe. Fission therefore represents both a scientific breakthrough and an engineering achievement, because it harnesses the forces inside the atom and channels them into a steady flow of energy that can be converted into electricity. Without the process of fission, nuclear power plants could not exist, and the entire concept of atomic energy would remain only a scientific curiosity. Understanding this process is essential, because it explains not only how the reactors generate heat, but also why safety systems and careful management are required at every stage. Fission is at once simple to describe and complex to control, making it one of the most fascinating subjects in engineering and one of the most important foundations for modern energy production. When discussing how a nuclear power plant works, it is important to understand how the process of nuclear fission is transformed into usable heat, because the entire purpose of the reactor is to convert the energy released from splitting atoms into thermal energy that can then be used for generating electricity. Each time a uranium-235 nucleus undergoes fission, two main forms of energy are released. The first is the kinetic energy of the fission fragments, which are the two smaller nuclei created after the split. These fragments fly apart at high speeds and collide with surrounding atoms in the fuel material. Their collisions transfer energy in the form of heat, and this heat gradually spreads through the fuel rods. The second form of energy released is the energy carried by neutrons and gamma radiation. The neutrons not only continue the chain reaction, but also deposit some of their energy as they slow down within the reactor. Gamma rays are high-energy photons that escape from the fission reaction, and when absorbed by reactor materials, they also contribute to heating. Together, these forms of energy cause the fuel rods to become very hot. The heat is then transferred to the coolant circulating around the reactor core. The coolant, which is often water under very high pressure, flows past the fuel rods and absorbs the heat generated by the fission reactions. In pressurized water reactors, the most common type of nuclear plant, the water inside the reactor core is kept under such pressure that it does not boil even at very high temperatures. This hot pressurized water is then directed through heat exchangers or steam generators, where it transfers its heat to a secondary loop of water. In this secondary loop, the water turns into steam, and the steam is what drives the turbines. In boiling water, reactors, which represent another major design, the water inside the reactor itself boils directly to create steam, which is then sent to the turbine. In both systems, the principle is the same. The immense energy released from fission becomes heat in the fuel rods. This heat is carried away by coolant, and the coolant, either directly or indirectly, produces steam. The conversion of nuclear energy into heat is therefore the central link in the chain that connects atomic reactions to household electricity. Without effective heat transfer, a reactor could not safely operate because the buildup of heat would quickly damage the fuel rods and reactor structure. This is why the design of coolant systems is one of the most important aspects of nuclear engineering. Engineers must ensure that the rate of heat removal matches the rate of heat production so that the reactor remains stable. The effectiveness of this system explains why nuclear plants can run continuously for months at a time, producing large amounts of electricity with only occasional refueling. It also explains why safety systems are necessary to maintain coolant flow even in emergencies. In simple terms, nuclear fission provides the energy, but it is the conversion of that energy into heat and then into steam that makes a nuclear power plant function as a source of power, rather than just a scientific experiment. This conversion demonstrates the fundamental similarity between nuclear plants and conventional fossil fuel plants, because in both cases, the ultimate goal is to create steam to spin turbines. The difference lies in the source of the heat. In one case, it is combustion of fuel. In the other, it is the splitting of atoms. This step in the process bridges the gap between nuclear physics and practical engineering, and it shows how the invisible world of atomic nuclei translates into the visible energy that powers the grid. The reactor core is the central part of a nuclear power plant where the fission process actually takes place and where the heat that drives the entire system is generated. It is a carefully engineered space that contains the nuclear fuel, the structural framework to hold that fuel in place, and the materials required to control and moderate the chain reaction. At the heart of the core are the fuel rods, which are long, slender tubes filled with small ceramic pellets of enriched uranium dioxide. Each pellet is only about the size of a fingertip, but contains enough energy to power a household for many months once it undergoes fission. These pellets are stacked inside metal cladding, usually made of zirconium alloys, which are strong, heat-resistant, and capable of containing radioactive fission products. Hundreds of these fuel rods are bundled together into larger units called fuel assemblies, and the core of a commercial power reactor contains many such assemblies arranged in a precise pattern to allow coolant to flow around them. Between the fuel rods are spaces that allow water or another coolant to circulate and carry away the heat produced during fission. The reactor core also contains control rods, which are critical for regulating the chain reaction. These rods are made of materials that absorb neutrons effectively, such as boron, cadmium, or hafnium. By inserting or withdrawing the control rods from the core, operators can adjust how many neutrons are available to sustain fission. If the rods are fully inserted, the chain reaction slows or even stops, while withdrawing them increases the reaction rate. This mechanism allows for fine control of the reactor's power output and provides a rapid means of shutting down the reactor in emergencies. Surrounding the fuel and control rods is often a moderator, which is a material used to slow down fast neutrons produced during fission so that they are more likely to cause further fission events in uranium-235. In most reactors, ordinary water serves as both the coolant and the moderator, but some designs use heavy water or graphite as moderators. The geometry of the core, the composition of the fuel, and the arrangement of rods and moderator materials are all optimized to ensure that the chain reaction remains stable, controlled, and efficient. The reactor vessel, a thick steel structure surrounding the core, provides additional strength and containment. It holds the fuel assemblies, control rods, and coolant under high pressure and temperature conditions. The vessel is designed to withstand intense heat, radiation, and mechanical stress over decades of operation. Instrumentation and sensors are also embedded in the core and vessel to monitor temperature, neutron flux, pressure, and other critical parameters, allowing operators to maintain safe and steady operation. The core is not a static system, but one that evolves over time as fuel is gradually consumed. During operation, Some uranium-235 nuclei are split, while new fissile materials such as plutonium-239 are created as byproducts. This means that the composition of the core changes, and the reactor must be periodically refueled to maintain efficiency. Typically, only a portion of the fuel assemblies is replaced at each refueling, while the rest remain in the core for another cycle. The reactor core is therefore both the most powerful and the most carefully managed part of a nuclear power plant. It is where physics, engineering, and safety come together to harness the energy of the atom in a controlled way. By understanding its structure and components, it becomes clear how a nuclear plant can produce enormous amounts of energy in a relatively small space while maintaining a high level of safety and reliability. Control rods and neutron moderation are essential aspects of a nuclear power plant, because without them, the chain reaction inside the reactor core would be unstable and impossible to manage. To understand their role, it is important to recall that nuclear fission occurs when a uranium-235 nucleus absorbs a neutron and splits, releasing both energy and additional neutrons. These new neutrons fly out at very high speeds, and if left unmoderated, they would be too energetic to efficiently cause further fission in other uranium nuclei. This is why moderators are required. A moderator is a material that slows down fast neutrons without absorbing them, allowing them to reach an energy level where the probability of inducing fission is much higher. Ordinary light water, heavy water, and graphite are the most common moderators used in reactor designs. In water-moderated reactors, which make up the majority of reactors in the world, the coolant itself doubles as the moderator. The water molecules slow the neutrons through repeated collisions, making them suitable for sustaining a controlled chain reaction. Without moderation, the efficiency of the reactor would be drastically reduced because most of the neutrons would pass through the fuel without causing further fission. Alongside moderation, control rods play the role of managing the number of neutrons available in the system. These rods are made of neutron-absorbing materials such as boron, cadmium, or hafnium, and they are inserted or withdrawn from the reactor core depending on the desired power output. When the rods are fully inserted, they capture a large fraction of the free neutrons, slowing down or even stopping the chain reaction completely. When the rods are withdrawn, more neutrons remain available to cause further fission, and the power of the reactor increases. The movement of control rods is not random, but is guided by precise calculations and monitoring systems that measure neutron flux and reactor conditions in real time. During normal operation, the control rods are partially inserted to balance the chain reaction at a steady rate that produces the required thermal energy. In addition to their role in daily operation, control rods are also essential safety devices. In the event of an emergency, they can be rapidly inserted into the core through mechanisms designed for quick action, shutting down the chain reaction almost instantly in a procedure known as a scram. This provides a reliable way to halt the production of heat and prevent the reactor from overheating. The interplay between neutron moderation and control rod absorption demonstrates the delicate balance required to sustain a nuclear reaction safely. Moderators ensure that neutrons are in the correct energy range to keep the reaction going, while control rods regulate the intensity of the reaction by adjusting how many neutrons remain active. Together, they form the foundation of reactor control systems, enabling engineers to operate nuclear power plants for long periods with stability and predictability. This dual system highlights the precision of nuclear engineering, where the invisible movement of tiny particles inside the atom is managed through carefully designed mechanical components. It also shows how nuclear reactors embody both simplicity and complexity, the simple principle of fission producing energy, and the complex arrangement of materials and controls required to manage it. Without moderators, the chain reaction would fizzle out, and without control rods, it could escalate beyond control. Only by combining both elements can a nuclear reactor function as a safe and steady source of power. The coolant system of a nuclear power plant is one of its most important components, because it ensures that the enormous amount of heat generated in the reactor core can be safely transferred away and used to produce steam without allowing the fuel to overheat. Inside the reactor core, as uranium nuclei undergo fission, the fuel rods become extremely hot. If this heat were not removed continuously, the rods would melt and the reactor would be damaged. To prevent this, engineers designed coolant systems that flow water or another fluid around the fuel assemblies, carrying the heat out of the core. In most modern reactors, the coolant is ordinary water, kept under very high pressure so that it remains liquid, even at temperatures far above the normal boiling point. This is the principle of the pressurized water reactor, where the coolant circulates in a closed loop through the reactor vessel, absorbs the heat from the fuel rods, and then transfers this heat to a secondary loop of water through a heat exchanger or steam generator. In the steam generator, the primary coolant heats the secondary water, which turns into steam that drives the turbine. This design keeps the radioactive coolant isolated from the turbine and generator system, reducing contamination risks. In boiling water reactors, the system is slightly different because the coolant itself is allowed to boil directly in the reactor vessel, producing steam that goes straight to the turbine. This design is simpler, but means that the steam passing through the turbine is radioactive, requiring additional shielding and precautions. Regardless of the type, the role of the coolant system is always the same: transfer heat efficiently and safely. The effectiveness of the coolant depends not only on its ability to absorb and carry heat, but also on the continuous circulation driven by powerful pumps. If the pumps fail, or if coolant flow is interrupted, the temperature inside the core rises quickly, which is why backup systems and emergency core cooling systems are always part of the design. Some advanced reactors use coolants other than water, such as liquid sodium, carbon dioxide, or helium gas, each with specific advantages. Sodium-cooled fast reactors, for example, use liquid metal because of its excellent thermal conductivity and high boiling point, which allows for efficient heat transfer at atmospheric pressure. Gas-cooled reactors use helium because it is chemically inert and does not become radioactive easily. Regardless of the chosen coolant, the underlying principle remains constant. The coolant must move heat from the core to the turbines while keeping the reactor stable. Heat transfer in this context is based on conduction, convection, and phase change. Conduction occurs as the fuel rods pass their heat to the coolant in direct contact. Convection then carries the heated fluid through the pipes, and in systems designed to generate steam, the phase change from water to steam allows large amounts of heat to be carried efficiently. Engineers design the coolant loops with redundancy, multiple barriers, and extensive monitoring so that any problem can be detected quickly. In summary, the coolant system is the lifeline of a nuclear power plant. It is the bridge that connects the microscopic world of nuclear fission inside the fuel rods with the macroscopic world of turbines, generators, and electrical grids. Without coolant, there would be no safe way to use the energy of the atom, and with it the heat of the core can be transformed into steady, usable power for cities and industries. The process of steam generation and the mechanics of turbines form the vital bridge between the nuclear reactions inside the reactor core and the production of electricity that flows into the grid. While the fission of uranium nuclei produces heat within the fuel rods, it is only through the controlled use of steam that this heat can be transformed into mechanical motion and then into electrical energy. The principle is conceptually simple, yet engineered with precision. Water is heated by the coolant system until it turns into high-pressure steam, and this steam is then directed through turbines that convert the energy of moving fluid into the rotation of massive blades. In pressurized water reactors, the steam is generated in a secondary loop, isolated from the radioactive primary coolant, while in boiling water reactors, the steam comes directly from the reactor vessel. In either case, the production of steam must be carefully regulated to ensure the correct pressure, temperature, and flow rate, because the turbine system is designed to operate within specific parameters. The turbines themselves are sophisticated machines that have evolved over a century of power engineering. They consist of a series of blades mounted on a shaft, arranged in stages, with stationary blades alternating with rotating blades. As the high-pressure steam enters the turbine, it expands and passes over the blades, causing them to spin. Each stage extracts part of the steam's energy, and by the time the steam reaches the end of the turbine, its pressure and temperature have dropped significantly. The rotation of the turbine shaft is then transferred directly to the generator, which produces electricity through electromagnetic induction. The efficiency of this process depends on the quality of the steam and the design of the turbine. High temperature, high pressure steam produces the greatest efficiency, which is why the materials used in turbine construction must withstand extreme conditions without degrading. Alloys resistant to heat and corrosion are used, and the blades are engineered to precise aerodynamic shapes that maximize energy transfer. Steam generation also involves important auxiliary systems. After leaving the turbine, the steam must be condensed back into water so that it can be reused. This occurs in the condenser, a large heat exchanger that uses cooling water from a river, lake, or cooling tower to absorb the remaining heat and return the steam to liquid form. This closed cycle conserves water and ensures continuous operation. The condensed water is then pumped back to the steam generator or reactor vessel, completing the cycle. The interaction of the reactor, the steam generator, the turbines, and the condenser creates a loop of energy conversion that can run for many months at a time without interruption. Turbine mechanics also include safety and control systems. Valves regulate the flow of steam. Bypass systems can redirect steam if needed, and monitoring equipment tracks pressure, vibration, and temperature to ensure safe operation. The turbines themselves are housed in reinforced structures to contain their motion and protect them from environmental conditions. When viewed as part of the larger system, steam generation and turbine mechanics illustrate how nuclear plants share fundamental similarities with fossil fuel plants. In both cases, it is steam that spins the turbines, and the difference lies in how the steam is produced. In coal plants, it comes from burning solid fuel. In gas plants, it comes from combustion of hydrocarbons. And in nuclear plants, it comes from atomic fission. The mechanics of the turbines remain largely the same, a reminder that while nuclear energy is based on advanced physics, the conversion of heat to motion relies on established mechanical engineering. This combination of nuclear science and classical turbine technology is what makes the nuclear power plant both complex and familiar, bridging the invisible world of atoms with the visible machinery of power generation. The electrical generator is the final stage in the chain that begins with nuclear fission, and it is the component that transforms the mechanical motion of the turbine into usable electrical energy that can be distributed across the power grid. While the nuclear reactions and the production of steam may appear more dramatic, the generator itself is based on principles of electromagnetic induction discovered in the 19th century by Michael Faraday. These principles state that when a conductor moves through a magnetic field, an electric current is induced in the conductor. In the generator, the rotating shaft of the turbine is connected directly to a large rotor inside the generator housing. This rotor is fitted with powerful electromagnets, or coils, supplied with direct current to create a strong magnetic field. Surrounding the rotor is the stator, which is a stationary ring of tightly wound copper coils. As the rotor spins, its magnetic field sweeps past the stator coils, inducing a flow of electrons and thus producing alternating current electricity. The amount of power produced depends on the speed of rotation, the strength of the magnetic field, and the number of coils in the stator. In a large nuclear plant, the generator is capable of producing hundreds or even thousands of megawatts of electricity, enough to supply entire cities. The process is continuous, and as long as steam flows through the turbine and keeps the shaft turning, the generator delivers a steady output. To ensure stability, the generator is connected to transformers that adjust the voltage to suitable levels for transmission over long distances. Electricity leaves the plant at very high voltages to minimize losses during transmission, and is later stepped down by additional transformers before reaching homes and industries. The generator must operate with high reliability and is designed to handle the enormous mechanical and electrical stresses of continuous use. Cooling systems are critical here as well, because the movement of electricity through the coils generates heat. Some generators use air cooling, while larger ones employ hydrogen or water cooling to maintain safe operating temperatures. The generator is also equipped with sophisticated monitoring devices that track vibration, temperature, electrical output, and other parameters to detect any irregularities before they become serious. In the context of the entire power plant, the generator represents the culmination of many steps: the splitting of atoms, the transfer of heat to coolant, the production of steam, and the rotation of the turbine. Yet it is the generator that delivers the actual product of the plant, the flow of electrical energy that powers modern life. Without it, the chain would stop at mechanical motion with no practical benefit. The role of the generator also highlights the link between nuclear technology and traditional power engineering. Although the source of the heat is unique to nuclear plants, the method of producing electricity is fundamentally the same as in coal, gas, or hydroelectric stations. This demonstrates the universality of turbine generator systems in modern energy production. By examining the generator, one sees how advanced nuclear physics is seamlessly connected to classical electromagnetic theory to produce a reliable supply of electricity. The generator is therefore not only a machine, but also a symbol of the way science and engineering work together, translating the smallest changes in atomic nuclei into vast amounts of energy that light up cities, run factories, and sustain daily life. Containment structures and safety barriers are among the most critical features of a nuclear power plant, because they are designed to ensure that radiation and radioactive materials remain isolated from the environment under both normal and accident conditions. At the center of the plant is the reactor vessel, a thick steel cylinder that holds the reactor core and the coolant. This vessel is the first barrier, designed to contain the fuel, the fission products, and the intense pressure and heat inside the core. Surrounding the reactor vessel is the primary containment structure, typically a large reinforced concrete building with walls several meters thick and often lined with steel. This structure is built to withstand extreme conditions such as earthquakes, floods, or even the impact of an aircraft, and its primary function is to prevent any release of radioactive material in the unlikely event of a major accident. The design philosophy of nuclear power plants is based on what is known as defense in depth, meaning that multiple layers of protection are built in, so that if one barrier fails, additional barriers remain to provide safety. Beyond the reactor vessel and the containment building, there are secondary structures such as the biological shield, a layer of dense material, often concrete, placed around the reactor to absorb radiation and protect workers. Ventilation systems are also equipped with high-efficiency filters that can capture radioactive particles before air is released outside. Another key safety feature is the cooling system redundancy, because heat continues to be generated in the core even after the fission reaction is shut down, called decay heat. Emergency cooling systems are in place to ensure that the fuel rods remain submerged and cooled at all times. These systems often include multiple independent pumps, backup power supplies, and passive cooling mechanisms that can operate without human intervention. In addition to physical barriers, safety also relies on monitoring and control systems. Sensors track temperature, pressure, radiation levels, and neutron flux continuously, and operators in the control room are trained to respond quickly to any deviations from normal operation. Automatic shutdown systems can insert all control rods instantly if critical parameters exceed safe limits, ensuring that the chain reaction stops immediately. The containment structures are also designed with pressure relief systems that can manage gases generated in the core without allowing uncontrolled releases. For example, in some designs, filtered venting systems allow steam to be released in a controlled way while trapping radioactive particles. These safety barriers have evolved over decades of engineering and lessons learned from past incidents. After the accident at 3 Mile Island in 1979, containment integrity and emergency cooling systems were strengthened. After Chernobyl in 1986, international standards emphasized robust containment because the Soviet RBMK reactors lacked such protective structures. After Fukushima in 2011, further improvements were made to ensure that plants could withstand loss of power and extended cooling challenges. Each generation of nuclear power plants has added new layers of safety to make containment more reliable. In summary, containment structures and safety barriers represent the interface between the highly energetic environment inside the reactor and the outside world. They demonstrate how nuclear engineering balances the potential of atomic energy with the responsibility of protecting people and the environment. The reactor vessel, the biological shield, the reinforced containment dome, the filtration systems, and the redundant cooling circuits all serve one purpose: to ensure that nuclear energy can be used safely and reliably. Without these barriers, the risks of nuclear power would outweigh the benefits, but with them, the technology has been able to operate for decades in many countries, delivering vast amounts of electricity with very few incidents. Radiation monitoring and protection are fundamental elements of every nuclear power plant because they ensure that both workers and the public remain safe while the reactor operates. Radiation is the energy emitted by unstable atomic nuclei in the form of particles or electromagnetic waves, and while it is an unavoidable byproduct of fission, it can be managed through careful design, shielding, and monitoring. There are several types of radiation relevant in a nuclear facility, including alpha particles, beta particles, gamma rays, and neutrons. Alpha and beta particles can be blocked by relatively thin materials, but gamma rays and neutrons are highly penetrating and require dense shielding, such as thick concrete walls or heavy metal barriers. Inside the reactor building, radiation levels are highest near the core, so shielding structures such as the biological shield and the containment walls are designed to absorb and reduce radiation to safe levels. Beyond structural protection, a comprehensive system of radiation monitoring is employed throughout the plant. Detectors are placed in key areas to measure gamma radiation, neutron flux, and airborne radioactivity. These instruments provide real-time data to the control room, where operators can immediately detect any abnormal rise in radiation levels. Workers are also equipped with personal dosimeters, small devices that measure the cumulative dose of radiation received over time. This allows strict control of occupational exposure, ensuring that no individual exceeds regulatory limits. In most countries, safety standards are based on international guidelines established by organizations such as the International Atomic Energy Agency and the International Commission on Radiological Protection. These standards define maximum allowable doses for workers and members of the public, and plants are designed to operate well below these thresholds. Radiation protection is not limited to shielding and monitoring, but also includes operational procedures. Access to high radiation areas is carefully controlled, and workers rotate duties to minimize exposure. Remote handling tools and robotic systems are used for tasks that would otherwise require direct human contact with radioactive materials. Ventilation systems equipped with high-efficiency filters prevent the spread of radioactive particles within the plant, and any air released to the environment is carefully filtered and monitored. Water used as coolant is also treated and contained to prevent contamination. Emergency preparedness is another critical component. In the unlikely event of an accident where radiation could escape containment, plans exist for monitoring the environment outside the plant, issuing protective actions such as sheltering or evacuation, and distributing iodine tablets to reduce the uptake of radioactive iodine by the thyroid. These measures are tested regularly through drills involving plant staff, local authorities, and emergency services. The importance of radiation protection extends beyond normal operation. During refueling outages, when the reactor is shut down and spent fuel is handled, additional monitoring is used to ensure safe working conditions. Spent fuel is stored under deep water in pools that provide both cooling and shielding from radiation. Later, it may be transferred to dry storage casks designed with thick steel and concrete walls. All these measures reflect the principle of keeping radiation exposure as low as reasonably achievable, often referred to as the ALARA principle. This principle emphasizes continuous improvement, careful planning, and constant vigilance to ensure safety. Radiation monitoring and protection illustrate how nuclear power combines advanced technology with a strong safety culture. The invisible energy of radiation is made measurable and controllable through instruments, procedures, and engineering, ensuring that nuclear energy can be used without endangering workers or the surrounding population. By maintaining multiple layers of monitoring and protection, nuclear plants demonstrate a commitment to safety that matches the immense power they harness, creating confidence that radiation, though powerful and potentially harmful, can be managed responsibly in the service of reliable electricity generation. Waste management and spent fuel storage are essential aspects of nuclear power because every reactor produces materials that remain radioactive long after the fission process has ended, and these materials must be handled with great care to ensure safety for people and the environment. When uranium fuel is loaded into the reactor core, it is in the form of small ceramic pellets arranged in long metal fuel rods. During operation, the uranium-235 atoms inside the pellets undergo fission, releasing energy. But after several years, a significant portion of the fuel becomes less efficient because many of the fissile atoms have been consumed and because fission products build up within the rods. These used assemblies are referred to as spent fuel, and although they are no longer efficient for sustaining a chain reaction, they continue to emit radiation and generate heat. This combination makes them both hazardous and valuable, since they contain not only radioactive waste, but also materials such as plutonium that could in theory be reused. The first step in managing spent fuel is temporary storage in the reactor building itself. Once removed from the core, the assemblies are placed in deep pools of water known as spent fuel pools. The water serves a dual purpose by cooling the hot fuel and by providing shielding from radiation. These pools are lined with thick concrete and stainless steel and are equipped with circulation systems that maintain water quality and temperature. Fuel can remain in these pools for several years until its heat and radiation levels decline. After this initial period, the fuel may be transferred to dry storage. In this method, the assemblies are placed in massive casks made of steel and concrete, designed to block radiation and dissipate residual heat. These casks are stored on site at the plant or at centralized storage facilities. They are engineered to withstand earthquakes, floods, and even impacts, ensuring long-term safety. Beyond storage, some countries pursue reprocessing programs in which spent fuel is chemically treated to extract usable uranium and plutonium for reuse in new fuel. This reduces the volume of high-level waste, but creates challenges related to cost and proliferation risk. Regardless of whether reprocessing is used, there remains a portion of waste that is highly radioactive and long-lived. This high-level waste requires secure disposal solutions. The most widely studied approach is deep geological disposal, where waste is placed in specially designed containers and buried deep underground in stable rock formations. Such facilities aim to isolate the waste for hundreds of thousands of years, long enough for its radioactivity to decay to safe levels. In addition to high-level waste, there are intermediate and low-level wastes generated by reactor operations, including contaminated tools, clothing, and filters. These materials are managed through established processes such as compaction, incineration, or near-surface disposal, depending on their radioactivity. Waste management is not only a technical challenge, but also a social and political one, since communities must agree to host storage sites and governments must ensure that future generations are protected. The principles guiding all waste handling include containment, isolation, and transparency. Containment ensures that radioactive materials do not escape their barriers. Isolation ensures that they are kept away from people and ecosystems. And transparency builds trust by providing clear information and independent oversight. In summary, waste management and spent fuel storage represent the long-term responsibility of nuclear power. They show that while the energy produced is immediate and useful, the byproducts require careful stewardship across decades and centuries. Through a combination of engineered barriers, scientific research, and regulatory oversight, nuclear energy has developed methods to manage its waste safely, but it remains an area of ongoing development and debate. The way in which waste is handled will continue to shape public perception and the future of nuclear power as a whole. The efficiency of a nuclear power plant and its comparison to other types of power plants is an important subject because it reveals both the strengths and limitations of nuclear energy in the broader context of electricity generation. Efficiency, in this sense, refers to how effectively the plant converts the energy contained in the fuel into usable electrical power. In most modern nuclear reactors, the thermal efficiency is around 30 to 35%, meaning that only about 1/3 of the heat produced in the core is ultimately transformed into electricity, while the rest is lost as waste heat through cooling systems. This efficiency level is similar to that of conventional coal-fired power plants and slightly lower than that of modern natural gas combined cycle plants, which can reach efficiencies of 50 to 60% by using both gas turbines and steam turbines in sequence. Despite this difference, nuclear power has unique advantages because its fuel has an extremely high energy density. A small amount of uranium can produce as much energy as tons of coal or barrels of oil. This means that fuel transportation and storage requirements are minimal compared to fossil fuels. In addition, nuclear plants can operate continuously for long periods, often 18 to 24 months before refueling, providing a stable and predictable source of electricity. Coal and gas plants require continuous fuel delivery, and their output can fluctuate with supply conditions. Hydroelectric plants can achieve higher efficiencies than nuclear plants, sometimes over 90%, but they are limited by geography and climate. Renewable energy sources such as wind and solar do not rely on fuel and have no direct emissions, but their output is variable and dependent on weather and daylight, requiring backup or storage solutions to ensure reliability. Nuclear power therefore occupies a middle ground, offering reliable baseload power with low greenhouse gas emissions, though with challenges related to efficiency, waste, and safety. When comparing environmental impacts, nuclear power is often contrasted with coal. Coal plants emit large amounts of carbon dioxide, sulfur dioxide, nitrogen oxides, and particulate matter, all of which contribute to climate change and air pollution. Nuclear plants do not produce these emissions during operation, making them far cleaner in terms of air quality. Natural gas plants emit less carbon dioxide than coal, but still contribute to greenhouse gases and can release methane, a potent greenhouse gas, during extraction and transport. Hydroelectric power produces no emissions during operation, but can disrupt ecosystems and displace communities. Wind and solar have very low environmental impacts during operation, but require land, materials, and energy for construction. From an economic perspective, the efficiency of nuclear power is balanced by high capital costs. Building a nuclear plant requires significant investment in safety systems, containment structures, and regulatory compliance. However, once built, the fuel and operating costs are relatively low, and the plants can run for 60 years or more with upgrades. Coal and gas plants are cheaper to build, but require ongoing fuel purchases and emit pollutants that impose health and environmental costs. Renewable sources have falling construction costs, but require integration into grids designed for steady power supply. Overall, nuclear power compares favorably in terms of reliability and low emissions, even if its thermal efficiency is modest compared to the best fossil fuel technologies. In practice, efficiency is not the only measure that matters, since energy policy considers cost, reliability, environmental impact, and long-term sustainability. Nuclear power remains one of the few options capable of providing large-scale baseload electricity without greenhouse gas emissions, and its efficiency while not the highest, is sufficient when combined with the unique advantages of high fuel density and continuous operation. This comparison shows why nuclear energy remains part of the global energy mix and why its role continues to be debated alongside other sources. The environmental impact of nuclear power and the way it is perceived by the public are deeply connected and have influenced the role of nuclear energy in global electricity generation since its earliest days. On one hand, nuclear power plants do not emit carbon dioxide or other greenhouse gases during normal operation, making them attractive in the context of climate change mitigation. Unlike coal plants, they do not release sulfur dioxide, nitrogen oxides, or particulate matter that cause air pollution and health problems. This clean operational profile means that nuclear power has a much lower environmental footprint in terms of air quality and climate impact than most fossil fuel sources. On the other hand, nuclear plants do produce radioactive waste that must be managed for very long timescales, and accidents such as Chernobyl in 1986 and Fukushima in 2011 have left lasting impressions of risk and danger. Even though such accidents are rare, they have shaped public perception more strongly than decades of safe operation in many other plants. Environmental impacts also include the use of large amounts of water for cooling. Nuclear plants often rely on nearby rivers, lakes, or coastal waters to dissipate waste heat, and this can raise local water temperatures, affecting aquatic ecosystems. The visible cooling towers and large plumes of water vapor have become symbols of nuclear energy in the public imagination, sometimes reinforcing the perception of environmental disruption, even though the vapor is simply steam. Land use for nuclear plants is relatively small compared to renewable energy sources such as solar and wind farms, which require larger areas for equivalent output. But the long-term storage of waste and the decommissioning of plants at the end of their life cycles present additional environmental challenges. Public perception is often shaped not by technical details, but by emotional and historical associations. In some countries such as France, nuclear power has been widely accepted and even embraced as a source of national energy independence, with the majority of electricity coming from reactors. In other countries, such as Germany, public opposition has been strong, leading to decisions to phase out nuclear power entirely. The contrast reflects differences in political culture, trust in institutions, and the weight of past events. Media coverage has also played a major role in shaping perception. Dramatic images of accidents or waste storage sites tend to dominate headlines, while the routine and uneventful operation of most reactors receives little attention. As a result, fear and uncertainty often outweigh the recognition of nuclear power's benefits. Environmental groups remain divided, with some opposing nuclear energy as inherently unsafe, and others supporting it as a necessary tool to reduce carbon emissions and combat climate change. The debate is further complicated by economic and social factors, including concerns about the cost of building and maintaining plants, the time required to construct new reactors, and the risks of nuclear proliferation. Advances in reactor technology and waste management aim to address many of these concerns, but public trust is not built solely on technical solutions. Transparency, clear communication, and a demonstrated commitment to safety are essential for improving perception. In summary, the environmental impact of nuclear power is relatively small in terms of emissions and land use, but significant in terms of waste and water requirements. Public perception, however, is often shaped more by fear of accidents and distrust of institutions than by measured evaluation of risks and benefits. This dual reality has made nuclear energy one of the most controversial yet vital parts of the global energy conversation. Its future will depend not only on engineering advances, but also on the ability of governments and industry to engage with the public honestly and responsibly, demonstrating that nuclear power can contribute to a cleaner and more sustainable world without compromising safety or the environment. The future of nuclear power is a subject of ongoing debate and innovation, shaped by the challenges of climate change, the demand for reliable electricity, and the lessons learned from decades of operation. Nuclear power today supplies a significant portion of the world's electricity, particularly in countries that lack large fossil fuel resources. But its future will depend on how well it adapts to changing needs and public expectations. One of the most important drivers of nuclear power's future is the global effort to reduce carbon emissions. As nations seek to replace coal and other high-carbon sources, nuclear energy offers a low-emission alternative capable of delivering large amounts of baseload electricity. Renewable energy sources such as wind and solar are growing rapidly, but their variability means that additional stable sources are required to balance the grid. Nuclear plants can provide this stability, running continuously for long periods without interruption. At the same time, the high costs and long construction times of traditional large reactors have led to interest in new designs that promise to be cheaper, faster to build, and safer. Among the most discussed innovations are small modular reactors, often called SMRs. These reactors are designed to be built in factories, transported to sites, and assembled more quickly than conventional plants. Their smaller size allows for greater flexibility in deployment, whether to power remote communities, industrial facilities, or to complement renewable energy sources. SMRs also incorporate advanced safety features, often relying on passive cooling systems that function without human intervention or external power. Another area of development is advanced reactor concepts, including fast breeder reactors and molten salt reactors. Fast breeder reactors are designed to generate more fissile material than they consume, potentially extending fuel supplies and reducing waste. Molten salt reactors use liquid fuel or coolants that operate at lower pressures and higher temperatures, offering potential improvements in safety and efficiency. Fusion power, the process of combining light nuclei to release energy, remains a long-term goal, with research projects such as ITER in France aiming to demonstrate its feasibility. While commercial fusion is still decades away, success would revolutionize energy production by providing nearly limitless power with minimal, long-lived waste. Waste management will also shape the future of nuclear power. Developing permanent geological repositories for high-level waste is essential to address long-term safety concerns. Countries such as Finland and Sweden are moving forward with such projects, demonstrating that solutions are possible with public involvement and careful planning. The role of nuclear power in combating climate change may also shift public perception. As the urgency of reducing emissions increases, some environmental groups and policymakers have begun to reconsider their opposition to nuclear energy, viewing it as a necessary part of a sustainable energy mix. At the same time, safety, cost, and proliferation risks remain major challenges. Building trust with the public through transparency, strict regulation, and international cooperation will be critical for expanding nuclear power's role. Economically, the future will depend on whether new reactor designs can reduce costs and construction times, making nuclear power more competitive with renewables and natural gas. Technological progress in digital monitoring, advanced materials, and automated systems may also improve efficiency and reliability. In summary, the future of nuclear power is neither guaranteed nor doomed, but will depend on a combination of technological innovation, political will, and public acceptance. If small modular reactors, advanced designs, and safe waste management solutions succeed, nuclear power may expand significantly as part of the global strategy to combat climate change. If costs remain high and public trust remains low, its role may decline in favor of renewables and other technologies. Either way, nuclear power will continue to be part of the energy conversation, representing both the promise of clean, reliable electricity and the challenge of managing powerful technology responsibly.